Hello, geometry students. Today we're going to talk about congruent triangles. When we say that true triangles are congruent, we all know that that means they're the same size and same shape. What that also means is there are 6 parts of a triangle, or there's 3 angles and there's 3 sides. So when we say that triangle cat, for example, is congruent to triangle dog, we mean specifically that angle C is congruent to angle D, angle A is congruent to angle O, and angle T is congruent to angle G. And you can see that the order that they're written, we've got the corresponding parts. We know that C goes with D because they're both first, and then angle A goes with angle O because they're both second, and angle T goes with angle G because those are both last. And that's called corresponding parts of congruent triangles are congruent because the C and the D are corresponding, and the A and the O, etc. But not only are the 3 angles congruent, we know the 3 sides of triangle cat are congruent to the 3 sides of triangle dog. For example, CA is congruent with DO, and we know that because CA is first and DO is first in that triangle. And AT is congruent to OG, and CT is congruent to DG. So for all 6 of these things, or if these triangles are congruent, these 2, we know that all 6 of these things are true. But when we go in reverse, it could also be said that if we know all 6 of those things are congruent, we know the 2 triangles are congruent. Well, we're going to see if there's a shortcut, or there's different shortcuts where we can say that the triangles are congruent, even if we don't know all 6 parts are congruent. So we're going to go through the different options. The first option is if we know that 3 sides of one triangle are congruent to 3 sides of another triangle, are the 2 triangles necessarily congruent? And I can demonstrate that they are. And I've got, if I change side 2, no matter what I change it to, I can see that they remain congruent. Side 1, the way I have it set up, is always going to be the same length as side 1, and side 3 is always going to be the same length as side 3. And you can see that the 2 triangles are always going to be the same shape and size, no matter how I move the sides. As long as the 3 sides are congruent, I know that the 2 triangles are going to be the same shape and size. So this is one of our shortcuts. It's called the side-side-side. You can call it a shortcut. Some people call it a side-side-side conjecture. Some people call it the side-side-side theorem. All right, but we know that that works. Basically, the idea is if 3 sides of one triangle are congruent to 3 sides of another triangle, then the triangles are congruent. Let's take a look at another option, which is side-angle-side. And the way this one is read is 2 sides and the included angle of one triangle is congruent to 2 sides and the included angle of another triangle, then the triangles are congruent. And the included means that the angles that are congruent happen to be right sandwiched in between the 2 congruent sides. So as you can see, this side is congruent to this side always. I've got it set. I can change the length, but they're always going to be congruent. And side 1 is congruent to side 1. I can change that length. And then the angle that's sandwiched between them, called the included angle, is also going to be congruent. I've got it set up where that stays congruent. And you can see that even if I change any one of these 3 things, that the 2 triangles are going to be, in fact, congruent. Let's see, can I grab? If I can grab that one and move it, you can see that they're going to be congruent. So we know that this is also a shortcut or a theorem or a conjecture that says that if 2 sides in the included angle of one are congruent to 2 sides in the included angle of the other, the 2 triangles must in fact be congruent. Let's look at our next option, which is similar to the last one, but this time it's 2 angles in the included side. And you can see on the picture that I've got these 2 angles congruent to these 2 angles. I can change that angle. I can also change both of them. As I move that point, both of those angles change together. And I can also change that side. I can see that those remain congruent. And if I were to take this triangle here, can I move it? If I pick the whole thing and move it over, we can see that the 2 triangles are going to be congruent as long as those 2 angles remain congruent to those 2 and the included side is congruent to that included side. So we know so far that side-side-side works, side-angle-side works, and angle-side-angle works. Let's look at a couple other options. This one is called side-side-angle or angle-side-side. This would be said two sides in the non-included angle. Okay. Now we can see in this triangle, I want this one. We can see that this side's congruent to this side, and this side's congruent to that side, and that angle's congruent. And I can move that one. I can't really do that, but I can change the length of that one. And we can see that it appears that with an angle and two congruent sides, that's going to be congruent to that one. But then we also have another option, which is option 1, or option 2. Which one is it? Wait a minute. Okay, I figured out my problem. We've got these two sides congruent. Let's go back to option 2. We can see that that side's congruent to that side there's congruent to that side, and that angle's congruent to that side, which gives us the side-side angle configuration. But what we could also do is show this option, which is, we can see that that's still congruent to that one, that side is still congruent to that one, and the angles are still congruent. But what we have are two options there. And we don't know which one that one's going to be. I can't swing that one around. But we can see we have two potential options. One of them is congruent to the other triangle, and the other one is not. So this makes a case for, we have to say that it cannot be determined. Just based on these three things, we have to say we can't determine whether they're going to be congruent every time or not. So that one does not work. Then we have, wait a minute, we have the angle side. This one's kind of a difficult one to show, but basically if we have two angles and a non-included side, now I don't have a second triangle here, but it was too hard to demonstrate. But what I can demonstrate is that there's only one possible triangle. If I have another triangle with this exact same side length, there's in those two set angles, there really is only one option, and that would be in this case right there. Okay, with those two given side lengths and that given, those two angle measurements and that given side length, there's only one possible triangle that I could come up with. I can't change. I can't have a second option like I did on the previous example. So bottom line is that two angles and the non-included side of one triangle is congruent to two angles and the non-included side of the other triangle. It is going to form congruent triangles. Let's look at our next option. Our next option is angle, angle, angle. We can clearly see that we have a triangle, a small triangle, and a large triangle. And on the small triangle, we can see that those angles are congruent, those angles are congruent, and those angles are congruent. However, it's obvious that one triangle is it's much larger than the other one. So even though they have the same shape, they don't have the same size. So by knowing simply that three angles of one triangle are congruent to three angles of another triangle does not in fact prove that two triangles must be congruent. I don't know what this triangle is doing up there. I couldn't tell you what that one's for. But anyway, we press on. And what I have. Okay, so this is one example that we talked about a while ago of two sides and a non-included angle. We said that it could not be determined that they'd be congruent. There is one exception to that rule, and that is when that angle that we have right there is a right angle. And then then they can be proved congruent. And a lot of times people call that the hypotenuse leg theorem. Whereas we have a right triangle with the hypotenuse congruent to the hypotenuse and the leg congruent to the leg. So even if I change that, they're still going to be congruent triangles. Still going to be the same. So that is an exception to the rule that we talked about over here. Over here we talked about the two possibilities, so we can't typically use side-side angle or angle side-side unless that angle is a right angle. Then we can conclude that they would be congruent triangles. Thank you for listening, and I hope you do well on this unit.